Welcome to All Things Photonics, a podcast about the physical science of light driving scientific innovation in the 21st century. I'm Joel Williams, Associate Editor at Photonics Media. Join us as we explore the latest trends in optics, lasers, microscopy, and spectroscopy. Each episode you'll hear from leading voices from across the photonics landscape, brought to you by Photonics Media. In a previous episode of All Things Photonics, it was our pleasure to speak with Lasernet US coordinator Chandra Brianne Curry. Based at the SLAC National Accelerator Laboratory, Curry is a physicist working with the Matter and Extreme Conditions instrument at SLAC's LINAC Coherent Light Source, or LCLS, X-ray free electron laser. The parameters of the laser system at SLAC are driving ongoing research in the area of fusion energy. The Matter and Extreme Conditions instrument employs a titanium sapphire double CPA laser system, which optimizes it for dense plasma studies. Though each boasts extremely high power capabilities, no two laser facilities in the Lasernet consortium are entirely alike. As we learn in today's episode, the Advanced Laser Light Source, or ALLS, located outside Montreal, is a truly distinguished facility. ALLS develops radiation sources spanning the infrared to very high energy and ultrashort-pulse X-rays. The facility, which consists of multiple laser systems, enables dynamic imaging of molecules and complex systems. Anything else that you might imagine as being made possible by a system that approaches 1 petawatt of peak power is also supported by the high-intensity system at the ALLS facility. ALLS is also the only Lasernet facility located in Canada. Open to users since 2005, the facility was financed through the International Joint Ventures Fund program of the Canada Foundation for Innovation. While ALLS increases access for users from around the world, it has also emerged as a hub of laser innovation in Canada. With this in mind, our guests today are Francois Légaré, Scientific Head of ALLS, Heide Ibrahim, Senior Research Associate and Project Manager at Institut National de la Recherche Scientifique, and Donna Strickland, Chair of ALLS's Scientific Committee from 2013 to 2018. In 2018, Strickland was named a recipient of the Nobel Prize in Physics for developing chirped pulse amplification with Gerard Moreau. We start our panel with Dr. Légaré on the specifications of the distinct laser platforms at ALLS. The conversation gives way to the benefits of ultra-high power systems, their applications, and the overall state of laser science.
The two platforms are basically based on two types of laser systems. So one platform has a really high peak power laser system with 2.5 hertz repetition rate, 13 joules of energy per pulse, 17 femtosecond pulse duration for a peak power of 750 terawatt, which is near the petawatt peak power. So this is really high intensity laser. While the other laser systems are more like high repetition rate. And in particular, we got in 2017 funding from the Canada Foundation for High Innovation and the Quebec government to get the most recent high average power ytterbium laser technologies. So here we are talking about repetition rate between 1 kilohertz and 100 kilohertz. And 100 kilohertz is 100,000 laser pulses per second. So obviously, the application that you do with the really high peak power versus the high average power are different. So now, with these laser systems, we couple them to end stations. And the end stations are to address specific scientific problems. For example, we have a beamline for laser wake field electron acceleration, where we generate really highly spatially coherent hard X-ray beam that we can use for a wide variety of application of phase contrast imaging. And then with the high repetition rate, for example, and I know Heide will discuss this today, we can do ultra-fast molecular imaging with these high rep rate system with coincidence imaging spectroscopy techniques.
Ultrafast molecular imaging is a core capability made possible by the ALLS infrastructure, and Heide Ibrahim is a leader in the field. Ibrahim and her team deploy a high-performance molecular camera to film the dynamics of atoms moving within molecular structures. The method is based on a principle of Coulombic explosion, which is itself induced by ultrafast laser pulses. Needless to say, the work benefits from an explanation.
So if you want to image molecules, the problem you're facing is they're extremely small and extremely fast, and you need to get these timescales and spatial scales together at the same time. And in terms of timescales, we are talking about femtoseconds, which is 10 to the minus 15 seconds, or billions of millions, I think, of a second. And at the same time, we are talking about nanometers or sub-nanometers in terms of spatial resolution. And the technique we are using for this is called Coulomb explosion imaging, in which case we are using 1 femtosecond laser pulse, which we have thanks to developments of Donna in the past. And these laser pulses, the first one can trigger a really fast motion, and then we are using a second one, which is blowing the molecule up. And this allows us to freeze motion at specific time delays. And once they are frozen, we can then read out the process in as long as time as our detectors need. And with this, we are able to really study individual molecules as they are moving. So we excite them and we study them. And because it's sensitive to individual molecules, we can even look at statistical processes. So we are not forced to have all the molecules working at the same time. And this is really a very new development we have been studying here at ALS, for example, in a process that is called roaming, in which case one molecular fragment really starts to walk off and circle its parent ion in the molecule or parent fragment of the molecule. But this is a process that is happening statistically, and we can study it one by one, and we can get the information of this together. No matter if there's a huge background or whatever, we can really select a specific motion in there. So this is one of the recent developments we have been looking at.
So ALS, of course, is a member of the Lasernet US consortium of 10 lasers. It's the only in Canada. And so while each laser system offers unique specifications and benefits as a result of different branches, different techniques within science, ALS is the only facility in Canada. And so it does have this sort of unique tie-in to scientific innovation taking place in Canada and beyond. And Donna Strickland is certainly equipped to speak about that. How does the facility support broader innovation, not just in terms of the techniques that it enables, but also on a geographic level, scientific progress in Canada?
Well, that's right. I think the point is now the lasers are getting so big that they can't be held in individual labs anymore. And it's, again, usually easier, especially now during COVID, it's definitely easier to travel within a country than to other countries. But I think it's important for our Canadian ultrafast scientists to have such a laser system that we can use on a fairly regular basis to help with all of these innovation sectors that we have in Canada and abroad. But I also think on a more global scale, it helps us be a player so that we can also go and use the other lasers. We can also attract the international collaborators to Canada with such a system. And that also helps both us as scientists, but also our students to have this larger view of what goes on in the field worldwide. And I think we will get to the point eventually, just like our astronomy friends who have to get together and decide, what telescopes to build, we will get to the point where we have to decide which lasers to build. And so we want to start really building these collaborations right around the world. And I think having this large laser facility in Canada helps with that. And it certainly helps us to be part of Lasernet US.
Lasernet US aims to increase access to laser systems neither found nor accessed elsewhere in North America. It is common for those seeking a certain system to enlist the help of the consortium to identify the best fitting laser system for their science. As Francois Légaré explains, at ALLS, the hard X-ray beamline is a much coveted system for data storage devices, quantum materials and structures, and material science.
With the hard X-ray beamline that we have at ALS, I'm aware that there's a user of Lasernet US that will come at our facility to look at ultrafast demagnetization in magnetic materials. And this is a very important research topic at the moment because people think about manipulating on the ultrafast timescale demagnetization to improve our data storage devices. So again, information and communication technologies. We are also working with an industrial partner to develop advanced metrologies for the characterization of quantum materials and heterostructure. Again, obviously, next generation optoelectronic devices. And then, of course, lasers are used in materials processing. So there's a lot of interest for the advanced manufacturing.
The history of ALLS predates that of the Lasernet US consortium by more than a decade. Planning for the system in the scientific community dates back to the start of the millennium. The facility opened to users in 2005, and since then it has played a pivotal role in the transfer of technology out of the laboratory and towards commercialization. Légaré gives a brief history of the facility.
ALLS was basically a dream that has emerged from the Canadian community. I remember I was a PhD student when this was discussed at the end of the 90s. And then in 2002, my colleague, Jean-Claude Kiefer, has led a big international consortium to get $21 million Canadian from the Canada Foundation for Innovation to establish the ALLS facility. And then in 2005, we got the first users coming at the facility. Since then, I think we have trained more than 250, 300 students, postdocs. We had a lot of industrial partners. Since 2015, 22 industrial partners have benefited from access to ALLS. So we have this has enabled to develop new technologies. And of course, since 2005, we have continued to work to further improve the facility. And I hope we will continue for another 25 years.
Though ALLS is the lone Lasernet facility in Canada, it is one of 10 facilities currently comprising the consortium, of which it maintains membership. Donna Strickland, who introduced chirp pulse amplification, ties the development of CPA to the reality of laser innovation occurring on a global scale. CPA, Strickland says, began in the US, which is to be considered Lasernet US territory. Still, North American scientists weren't the quickest to run with the new technique, Strickland points out. The importance of Lasernet US lies in the importance of staying active and staying competitive.
If we're going to all have these laser facilities, and they're going to be big, we are going to have unique capabilities at each one. But I think when you talk about Lasernet US, it really is a response to the fact that CPA began in the United States, but somehow Asia and Europe really grabbed hold of it and ran with it maybe more than we did in North America. And so the Lasernet US really is a response to that, to say, all right, it started here and there's good reasons to have high intensity lasers. Let's get back in the game and let's start working together. Because certainly Europe worked together to build their big facilities, and Asia works together to build their big facilities. And so I think that's what's important. But I think, of course, we all watch what each other does. And if somebody comes up with a breakthrough, we're going to all want to use it and make sure we have the best lasers out there.
Right.
And I can add on to this. For example, in China, they have now projects to go to 10 petawatt and even beyond. Okay. At ALLS, given, let's say, the budget limit that we have, building such a facility requires huge amount of funding. And also driven by the fact that we want to use our lasers for the key innovation sectors of Canada, most probably in the near future, we will upgrade the capability of our high peak power laser system with repetition rate instead of energy. So instead of having 2.5 pulse per second, maybe with the new technologies, we could go to 10 or even 20 pulses per second. And at the end, the user using the X-rays for doing biomedical imaging will have more photons per second and will be able to take more measurements, more sensitive measurements. So as Donna said, it's very important to work together in order to not duplicate our capabilities, but to be complementary in terms of capabilities.
Lasers are light sources at a fundamental level. Though not all light sources deliver an infrared beamline using 100 Hz laser, as is the case at ALLS, there are other types of light sources in existence. A synchrotron is one of these alternative light sources. and there are some similarities to the massive systems that comprise the LaserNet consortium, especially ALLS. A synchrotron is a powerful X-ray source, just like the LWFA-based X-ray beam at ALLS. We asked about the difference between the beamline and a synchrotron light source, and we found out there is more than one.
With lasers, we have the temporal resolution. So the lasers are producing pulses, so very short flashes of light. So for example, the 750 terawatt laser system that we have at ALS, the pulse duration is 17 femtosecond. It's the shortest high peak power laser within the Lasernet US consortium and among probably one of the shortest in the world. So its unique specification is really very short pulse duration. So yeah, compared to synchrotron, we provide very short pulses. In addition, regarding this high power laser system, I've mentioned that we can generate hard X-rays with this laser. The hard X-ray source that is produced is highly spatially coherent. So the spatial coherence of the source enables researchers to perform phase contrast imaging with really high spatial resolution. So for example, one of the first LaserNet user that came at the facility is Professor Hamina Hussein from the University of Alberta, and she's basically using the X-ray source to look at the pores within some alloys with really high spatial resolution, really high throughput, with an application related to advanced manufacturing. So I will say pulse duration, and of course, one major aspect is the cost of installation and operation. If you compare a laser system, even a really high peak power laser system it would be a few tens of $millions of investment to build such a laser system. Compare with the next generation synchrotron or more like $1 billion machine. And obviously a synchrotron will have hundreds of employees, while a laser facility will be a team of 10, 15, 20 employees. So the size is simply not the same in terms of budget, but the science also can be very different because of the temporal resolution and the laser peak intensity.
The inner workings of technology transfer from a high-intensity laser system to a commercial product is complex, and so it was a question we were eager to ask. How does research, often at such a nascent stage, factor into something available for purchase? Part of it involves having numerous partners in industry working at various stages of development. ALLS has partnered with more than 20 Canadian companies since 2015 for just this purpose. Another part is using the laser system to refine and optimize methods and techniques that already exist. According to Légaré, there is a path to the X-ray and terahertz sources produced at ALLS to become integrated into commercial laser solutions.
Since 2015, we had 22 industrial partners. One of them, a spin-off company based at INRS near Montreal, where we are, FueCycle, is doing the commercialization of a system called holocore fiber to further reduce the pulse duration of lasers. So this is a technology that we have put in place at ALS, that we have improved, and now it's commercialized by a spin-off company. There's also other companies that are coming at us, for example, to test their instruments, to confirm the specifications of their instruments. There's a company called Things Photonics. They are building and commercializing streak cameras. And whatever a customer buy their expensive camera and the niche product, they need to characterize it before shipping it to the customer. So they come at ALS. And then in the recent years, we had also other industrial partners that came to us to push the development of technologies, including electron accelerator for ultra-fast electron diffraction imaging, for the characterization of quantum materials. And I believe in the near future, these X-ray sources that we produce, these terahertz sources that we produce, they will become well-engineered systems that could be fully integrated to commercial laser solutions and then be installed in a manufacturer And we are all aware in the US, for example, Intel is really interested in using the X-ray sources that we are producing with our lasers to look at their manufacturing process. So the future is bright for lasers.
With the innumerable capabilities of high-intensity lasers comes innumerable possibilities for them. And who better to ask about some of these possibilities than Donna Strickland? The X-ray pulse application that Strickland identifies as most intriguing right now speaks to the versatility of the high-intensity lasers, such as those found at ALLS.
Well, one of the ones that I like that's already started at ALS, and I don't think we've mentioned it yet, is the agriculture. And obviously right now we're all going to be worried about the fact that there's not going to be enough to go around this year because of world events. But, it's hard to believe that the X-rays that are produced at ALS is being used to study how nutrients get into the roots without ever taking them out of the dirt. And I think there's these kinds of innovations, whereas agriculture has also been studied for centuries, but we're bringing new techniques to help that out. And I think it could be applied probably much more widely into the agriculture to start looking to see how to improve produce and the efficiency of making it for this global demand that we have and are having to deal with things, both wars and with the environmental changes. It's going to be a big concern. And I think it's a strange thing that X-rays from lasers could help with that.
It's time for the Luminary Minute, a segment where Photonics Media looks back at a pivotal figure in the history of optical and photonic science. In this episode, we'll be talking about Theodore Maiman, the inventor of the laser. Maiman began his career in 1956 at Hughes Aircraft Company in the Atomic Physics Department, where he led the Ruby Maser redesign project for the U.S. Army Signal Corps. The work brought the device from a 2.5-ton cryogenic device to just 4 pounds. The successful downsize would serve to kickstart his laser project, which Maiman was able to convince company management to fund in 1959. At this point, there was a veritable race to develop the first laser, with groups at IBM, Bell Labs, MIT, Westinghouse, RCA, and Columbia University all vying for first place. Those groups held doubts about Maiman's decision to pursue a design using a synthetic ruby. However, their work was propelled by a 1958 paper by Arthur Shallow and Charles Hardtowns, in which Maiman identified multiple flaws. Confident in his analysis, Maiman moved forward with a design using a synthetic pink ruby as the active laser medium and a helical xenon flash lamp as the excitation source. Maiman successfully fired his laser on May 16, 1960. The date is recognized by UNESCO as the International Day of Light, which is celebrated with numerous laser and light-related events worldwide. The best way to avoid being inconvenienced by something unessential is to get rid of it entirely. That isn't always possible, of course, nor is it always practical. Give and take is vital to the ability of humans to coexist with one another. Increasingly, humankind has more with which it must coexist. In a world clamoring for autonomous solutions, humans and robots are on course to meet with nothing short of regularity. In the experimental soft matter physics group at the University of Luxembourg, group leader Professor Jan Lagerwall has collaborated to introduce a materials-based solution to this societal reality. Using cholesteric liquid crystal shells, the solution serves as an alternative to sensory inputs and computational power that are often combined to allow robots access to human-populated environments. Cholesteric spherical reflectors, or CSRs, are made to function in a way that is like the retroreflectors found in certain cars, road signs, and clothing. The CSRs, like retroreflectors, send light back to the source regardless of the direction along which they are illuminated. The solution is especially pertinent in a world with autonomous vehicles. At the core of this work are liquid crystals. In our conversation with Dr. Jan Lagerwall, we hear how applications for liquid crystals extend far beyond displays. In fact, sensors, semiconduction, and manufacturing are suitable applications. That conversation, as we conclude Season 5 of All Things Photonics, is next.
All right, we're speaking with Dr. Jan Lagerwall of the University of Luxembourg, and we're speaking about liquid crystals and soft matter photonics. First question, this is a sort of a question to get us on track. Let's talk about the different phases a liquid crystal can adopt, because there are several, and also some of the advantages to working with liquid crystals in each of these various states. Dr. Lagerwall, what are the different phases a liquid crystal can adopt?
That's actually a big question, so I'm going to try to answer it shortly. When I was a PhD student, I actually started counting how many liquid crystal phases there are because I was setting up a database for organizing them. And when I got to 100, I stopped. So it's simply, there are so many types of materials that form liquid crystal phases. And in each one, you have various subcategories. So it's actually enormous, and it's surprising how many there are. There are a couple of features that come back, and there are some that are, of course, much more important than others. So the classic one that is the most important, it's called the nematic. It comes from Greek nema for a thread, because that's a typical feature of the textures. And it is a liquid. It flows very easily, and it has no so the molecules have no long-range positional order. So it's called a liquid crystal because it has crystal-like characters, but a solid crystal, you have the molecules on a lattice. So there is a particular positional order, and that doesn't exist in the nematic. But what you have is orientational order. So all of the molecules are oriented in the same orientation. And that gives you the anisotropic properties or some of the anisotropic properties that you find in solid crystals as well, but it flows. So that's the most basic and most applied liquid crystal. So if you have a liquid crystal screen, a display like a laptop display or a TV display, most of them are still LCDs, that's going to be a nematic inside there. We work a lot with a chiral version of that chiral nematic, which is also called cholesteric because it was originally discovered in a cholesterol derivative. And what happens then is that you have the same type of ordering, the molecules organize in the same direction, but this direction now rotates in a helical fashion. So if you take this direction of ordering, that's called the director, and you take an axis perpendicular to it, then that's like a screw axis or a corkscrew or helix in spiral staircase any way you want, right? So if you imagine yourself walking up a spiral staircase, every step in the staircase, that gives you the molecular orientation at that point, so to speak. The reason that this spiral staircase is interesting is that the pitch of the staircase is often on the order of a few hundred nanometers, and that's why it's interesting for optics, because that means that you have a periodic structure with a period on the order of light wavelengths, and that gives you very interesting optical properties.
Part of the motivation for asking the question is in this interview, I hope that we are going to be able to, and I think that we will, talk about liquid crystals beyond the LCD, so to speak, because everyone knows liquid crystals are pivotal for advanced display technology, not just your conventional displays, 3D tech as well, but there's a lot more to it. And you mentioned the cholesteric phase, working with cholesteric liquid crystals. What are some of the advantages to working with liquid crystals in that form? Because that is a big part of what your group has been able to do.
Yeah, so I'm in love with cholesterics. It's probably the most fabulous phase I know because it's beautiful. It gives all these spectacular colors, but there's so many things you can do with it. And this combination of something being liquid and at the same time self-assembling in such ways is fantastic because it's liquid, we can process it like any liquid. So we use a technique called microfluidics, where we flow one liquid inside another. And you can do tubes, you can do droplets, you can do shells, and so on in that way. And another technique we use is called electrospinning, and then you spin fibers with the liquid crystal inside and so on, right? So because it's a liquid, we can process it into these different shapes and in different form factors, if you like. And then in each of these forms, the self-assembly then takes place. So you can get then a cylindrical fiber with this helix developing perpendicular to the fiber axis, or you can get a shell with a helix developing perpendicular to the shell radius or a droplet and so on. And if you take the cholesteric with a pitch in the order of a few hundred nanometers, that means that you get a Bragg diffraction element with spherical symmetry or with cylindrical symmetry. And that gives rise to a lot of very interesting optical properties, actually.
And those properties are properties that you're exploring in your group. And the applications are fairly vast in addition to being sort of outside of the regular norm LCD realm. Pretty vast, pretty diverse applications. And I want to talk about a couple. Let's start with sensing. You published a paper about 6 months ago. But let's talk about that paper, because liquid crystal sensing is not a mainstream application, certainly not yet, but it's an area that you've prodded with your group.
Right. So one of the nice things with liquid crystals is that soft matter in general, and I would say liquid crystals in particular, are very responsive materials. That means that you have a small external stimulus. It can be light, it can be electric field, it can be a magnetic field, it can be a mechanical disturbance or a chemical that is dissolved. And it can give a very strong effect on the self-assembly. And in fact, I should add, by the way, to your first question about which liquid crystals there are, one of the most important liquid crystals is us, ourselves. So every cell membrane in our body is in a liquid crystalline state. That's actually very important. And an example of how responsive liquid crystals are is that the cell membrane really depends sensitively on temperature and pressure and so on. That's one of the examples that, for instance, fish living really deep in the ocean, you cannot just bring them up to the surface, because then it's a different phase, a different behavior. And it's a little bit the same thing here, that we have our liquid crystal that we prepare in a certain way. And we know then that if you don't expose it to anything abnormal, it will have a certain color, or it will be transparent, or it will scatter light, or something like that. But then we prepare it in such a way that if it's exposed to, for instance, toluene gas, that's what we were working with in this paper, then it actually changes the way the molecules organize inside the fiber in this case. And that changes the optical properties. So in the first paper we studied in this, it was kind of on-off transition. So when the fibers were exposed to toluene, they lost their order completely. So it went from this nematic or aligned liquid crystal to a regular isotropic liquid. And that meant that we went from a scattering state to a transparent state. And now in the new paper, we fine-tuned this a little bit more. So we didn't just look at this on-off threshold, because in reality, it isn't on-off. There's a lot of happening before the transition to the isotropic state. And that's what we were monitoring. So in this case, we were simply measuring the birefringence of the liquid crystal as a function of toluene exposure. We were simply looking at it in a polarizing microscope. For the optics community, probably they know what the birefringent material look like in a polarizing microscope. By monitoring the color, we could actually establish how much toluene the system was exposed to.
I'll walk back here a little bit and give you a personal anecdote. It was about this time last year, early May 2021, we picked up a press release. The future is now. How can humans and robots live together? Interesting headline. And then we read it. And this is from the University of Luxembourg. And it went in a different direction than I think any of us expected. It brought us to an advanced functional materials paper. But that really is the question. How can humans and robots live together? And there is a liquid crystal materials-based solution to help answer that question as well.
Yeah, so that's, again, a very fascinating application of these cholesteric liquid crystals. So that paper, or that press release, was focusing on giving the world, let's say, a graphical encoding that humans cannot see, but robots can see very well. Because autonomous robots have difficulties to navigate in a regular environment, because it's difficult for a robot to, especially like if you have a window or a mirror, that's really, really tricky for a robot to figure out what that is. And then, of course, in general, if you have people there, you have cars, you have cyclists, and so on, and there's a lot of going on, and the robot has to figure out what is what. Most approaches to getting autonomous robots to be safe, and self-driving cars are autonomous robots. Many people don't realize that this is a robot, but it is to have artificial intelligence, and that works very well. But it's, of course, computationally intensive, and the computation uses up a lot of energy and so on. So in research, quite a few robotics researchers, they use a different approach. They put up markers. They look a bit like QR codes, so black and white markers, and they put them on the environment. So a door is marked up with a certain marker, a window is marked up with another marker, a box that the robot is supposed to manipulate is marked up with a third marker, and so on. And each of these markers then tell the robot, first of all, what is it? It's a door, it's this particular box, it's that box, and so on. But then because of the shape of the marker, you think of a QR code that is a bit simplified, and now you look at it from a certain angle, and then the QR code doesn't look like a square anymore because you're looking at it from an angle, right? And what the robot does is it just analyzes how far away is it from a square, and it can then calculate what is the angle. And by looking at the size of the marker, it can see how far am I away from this. So very simple image processing allows the robot to figure out what is it dealing with, where is it, and how is it oriented with respect to itself. So it's a very powerful system, but these are black on white, and they're usually printed like a US letter sheet of paper, quite big. So these are fine in a research lab, but you don't want to have this in your home or in a restaurant or in the city center and so on. So what we were doing in that paper, and we're working together with robotics collaborators both here and in Luxembourg and in the United States. Matthew Schwartz at New Jersey Institute of Technology is my main collaborator since many, many years on this, is to make these types of markers, but using, instead of black pigment with which you print black and white markers, we use these cholesteric spheres. I mentioned before that we can mold the cholesteric liquid crystal into a sphere using microfluidics. And then after we have done this, we polymerize the cholesteric liquid crystal. So we use the liquid state for making the shell and getting this self-assembled photonic structure, but then we freeze that state into a solid so that we can use these spheres afterwards any way we want. And the spheres are then tuned to reflect, to have a fairly little bit longer pitch or a shorter pitch than you need to see visible reflections. So it's, as I said, it's a spherical Bragg reflector. And let's say if we tune it for 380 nanometer, for instance, that's just outside the visible spectrum into the near UV. So it's not dangerous. The sunlight has a lot of 380 nanometer light, but we cannot see it. So if you tune them to reflect in that range, then these are invisible to us, but we can lay them out in the patterns of these markers. And then a robot that can see 380 nanometer wavelength light can then see these patterns. And why humans and robots can coexist is then basically you could decorate any environment, even human populated environment, with these types of markers because we don't see them, so they make no difference. But the robots can now, with much, much easier computation and with quite a bit more reliability also, navigate and figure out what they are dealing with.
Within sensing and outside of it, there are additional applications for liquid crystal structures. Both in the R&D and in application, these materials boast physical abilities that are useful for optoelectronic devices and surfaces. In his own group, Lagerwall is also investigating emerging applications specifically in the realm of material science.
There's a lot of work on making LEDs and photovoltaic cells and FETs, field effect transistors, and so on, using organic materials. And there you can take advantage of this liquid crystal self-assembly to get very ordered structures in these devices. So there are some people who use materials, so organic conductors and organic semiconductors, but they can form liquid crystal phases, and they use this to try to get better organic LEDs and so on.
I'd like to end with giving you an opportunity to preview or foreshadow some work that may be ongoing or forthcoming in your group. We've talked about fibers, we've talked about rubbers. There are a number of different materials applications for some of these liquid crystals, regardless of phase. Anything you'd like to preview for our listeners?
Yeah, sure. So maybe going back to the fibers or to the LCEs, or the rubbers a little bit. I didn't say so much about them, so why they are interesting. When you combine the liquid crystalline organization with a rubber, you can get some quite interesting effect. We work with several of these. On the one hand, if you change the temperature, for instance, so that you induce a phase transition from an order to a disorder state, then this rubber can completely change its shape. So it's kind of like an artificial muscle. But then you can also work in reverse and instead subject the rubber to mechanical strain, and then let the order in the rubber illustrate that strain. So this is something that we've been working on quite a lot recently, where we've made these rubbers with this cholesteric structure. So again, they reflect color because of Bragg reflect color. So often you say it's structural color. So especially if you take a sheet or a fiber that starts out reflecting red light, if you stretch this, because rubber has approximately constant volume. So if you make it longer in one direction, it has to get shorter in the perpendicular direction. And that means that this periodic helical structure, if it had a pitch to reflect red light in the beginning, now because it's compressed, it's going to reflect orange light, yellow light, green light, blue light, eventually violet light. And that means that just by looking at the color change, you can actually analyze the strain in the system. And because this is continuous, so we are doing this in two ways. We are doing it on the one hand in fibers that you can sew into a cloth, so you can use it for wearable technology. And we hope that we will also be able to weave fabrics out of this. So you could then really, for instance, sports people or also in medicine, it might be quite interesting to see where a certain strain or pressure is applied. But another quite fascinating example is you can make these you can make sheets out of these, so rubber sheets. And the nice thing with those is that they start out with uniform color, for instance, but if there is a local strain somewhere, then you see exactly where that strain is, and you can measure how strong it is because it's completely continuous. And there is a very important field called structural health monitoring that is very important these days because the infrastructure is going bad almost everywhere, and you have a lot of houses that are developing cracks and so on, right? So it's interesting to be able to monitor where a crack is forming. So when you make a new concrete building, there are actually micro cracks everywhere. That's natural. The danger happens when the cracks start growing beyond a certain dimension. So we're working with a professor here in Luxembourg. She is an expert in concrete and concrete stability and so on. And the idea is we're going to put these rubber sheets on a concrete block where there may be crack formation. And the idea is then that originally everything will be red, for instance, but if a crack grows, you can then see exactly where this crack is because it becomes green or even blue and so on. And this is independent of where in the sheet it happens. So the standard strain sensor for structural health monitoring, they are basically fibers, and you get one value per one sensor. So if you have a crack happening next to a sensor, you're not going to notice that crack. So in this case, we get a completely continuous monitoring of the crack formation.
That concludes this week's episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to our news editor, Jake Saltzman, as well as to this week's sponsors. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, and let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website, photonics.com.